Hello everyone, welcome to my channel Clear and Concise. In this video, I am going to explain you about free expansion process. Expansion of fluid against vacuum is called free expansion process. In order to demonstrate the free expansion process, let's consider an insulated container which is divided into two compartments where one compartment is completely filled with gas while the other one is completely evacuated. Now let's assume the initial state of gas in the container is described by using its pressure, volume and temperature. On PV diagram, it is denoted by state 1 by using its pressure P1, volume V1 and temperature T1. If we remove the barrier from the container, the gas rapidly expands to occupy the whole volume of container until the pressure in the system becomes uniform. Now, the final state of gas is represented by using pressure, volume and temperature. As this is an expansion process, the pressure in the system reduced from P1 to P2 and the volume in the system increases from V1 to V2. So, the final state is represented by pressure P2, volume V2 and temperature T2. We can have the information only at initial and final states of the process. As this is a rapid and spontaneous process, we don't have any information in between the initial and final states. So, we can only represent initial and final states on the PV diagram. Let's understand why do we assume insulated condition in free expansion process. Our main objective is to understand free expansion process. If the heat is considered, the process will get affected. Apart from that, most of the rapid processes are adiabatic in nature and slow processes are assumed to be isothermal. If the process is adiabatic, then there is no heat transfer from the system to surroundings or surroundings to system. So, we assume insulated condition with no heat transfer between system to surroundings. Now, let's understand why is it called free expansion. System generally does work to overcome the resistance. As vacuum doesn't offer any resistance against expansion, work done in this process is zero. So, it is called free expansion process. In thermodynamics, heat transfer and work transfer are boundary phenomena. Especially in free expansion process, neither heat crosses the boundary nor work is done on the system or done by the system. So, both are equals to zero in free expansion process of ideal gas actually. Now, by using first law of thermodynamics, Q minus W is equals to delta U, where U is internal energy of the system. Delta U denotes change in internal energy of the system. We have Q is equals to 0, W is equals to 0. So, delta U is equals to 0, which implies U2 minus U1 equals to 0. That is U2 is equals to U1. So, the internal energy of the system remains constant. U is constant in free expansion process. U is constant in free expansion process. The internal energy of the ideal gas is defined as U is equals to Cv times temperature T. Here Cv is specific heat at constant volume. Now, for free expansion process, initial internal energy of system U1 is equals to Cv times temperature T1 and final state U2 is equals to Cv times T2. We have seen for free expansion process, U2 is equals to U1. So, Cv times T2 is equals to Cv times T1. Cv gets cancelled. It gives T1 is equals to T2. So, we can say that free expansion process is also an isothermal process. It is an isothermal process. For closed system, TdS is equals to du plus PdV. If it is a free expansion process, then we have du is equals to 0. Now, equation reduces to ds is equals to P by T times dV. If we consider ideal gas, then PV is equals to nRT, which yields P by T is equals to nR by V. Now substituting that in place of P by T, we yield ds is equals to nR by V times dV. By integrating both sides, we yield integration of ds is equals to nR is constant, so taking out of the integration, nR times integration of dV by V, which yields S2 minus S1, that is delta S, equals to nR times integration of dV by V over V1 to V2 yields ln V2 by V1. We know V2 is greater than V1 for free expansion process, so this whole term is greater than 0, which yields delta S greater than 0. Entropy is greater than 0 for irreversible process. So we can say that free expansion process is an irreversible process because change in entropy is greater than 0. For closed system, H is equals to U plus PV, where H is enthalpy of the system. For ideal gases, PV is equals to nRT. Substituting that in the above equation yields H is equals to U plus nRT. Now, for free expansion process, we know U1 is equals to U2 and T1 is equals to T2. So, by obtaining H2 minus H1, we have U2 minus U1 plus N is constant and R is constant, taking them out, nR times T2 minus T1. We know delta U is equals to 0 for free expansion process and T1 is equals to T2. So, by substituting those two, we will have H2 minus H1 is equals to 0. Therefore, enthalpy is equals to constant in free expansion process. Enthalpy is constant in free expansion process. Summarizing the free expansion process. For free expansion process, work done is equals to 0, Q is equals to 0 and internal energy is constant. Similarly, enthalpy is also equals to constant and it is a isothermal process, that is T1 is equals to T2 and it is a irreversible process where delta S is greater than 0 and one most important thing is integration of PdV is not equals to 0. Remember this, integration of PdV is not equals to 0 but work done is equals to 0. You may be tempted to calculate work done in the process by using integration of PdV as volume is changing, but you cannot use this formula because it is applicable only to quasi-static process. But pre-expansion process is a rapid and spontaneous process, so we cannot use integration of PdV in order to calculate the work. But remember, that is not equals to 0. So, in this process, work is equals to 0, but integration of PdV is not equals to 0. The whole discussion holds true only for the ideal gases. Please do subscribe to the channel for more interesting videos. Thank you.